Swayam Prabha. Digital India. Educated India.
The last class we looked at Fugate approximations using aircraft linearized equations of motion around an equilibrium state. Now we will continue with our approximations, so called literal approximations, okay. And last class also we did Fugate approximation. We assumed that when the Fugate mode the aircraft is showing the Fugate mode, there is hardly any change in angle of attack, right. So, here in the short period mode approximation, the assumption is that remember we are trying to come down to simpler models so that we can work something out analytically. Otherwise, if you can solve the quartic equation, you can get exact expressions for Fugate mode eigenvalue and the short period mode eigenvalue, but it is not possible to solve analytically, right. And why we are doing it? Because we want to relate the perturbed motion of the aircraft with some design parameters, right. Otherwise, you can solve it numerically on computer, and probably you will have to work with a lot of parameters in the A matrix, change them, see how the roots are moving, right. You have to carry out that exercise. But the question is how do you do that? You are still trying to talk about the phase when you are designing an aircraft, and trying to see how the geometric or the aerodynamic parameters of the aircraft are affecting the motion, right. This we are thinking at the design stage. That is where these simpler models help. Now, assumption involved here is that when aircraft is showing short period behavior, there is hardly any change in the forward speed, right. So, we can set this to 0. When we do that, so there is no change in the forward speed from the equilibrium state. This delta u is from the equilibrium state, isn't it? Right, and motion is can we say is pitching, as an right. Okay. Now, with this assumption, I can reduce my 4 by 4 longitudinal linearized aircraft dynamic equations of motion to a 2 by 2 the equation in two variables, and those are the variables involved here are delta W, right, and delta Q. And when we are looking at stability, we are actually looking at the free response, right. So, we are not applying any control. So, the model, the simplified model for short period mode approximation is this. ZW U naught MW plus right. We can also write these equations in terms of delta alpha, right. I know how to write delta alpha in terms of delta W, and so you can rewrite the equations. So, this same matrix is for the short period case, right, with this assumption in the background. Now, I have to find out the eigenvalues of this matrix, and that eigenvalue will be corresponding to this particular mode. This will result into two values of lambdas, complex and complex conjugate lambdas, right, and it will come from this equation. So, what I do is I directly write down the expression for the frequency and the damping ratio. remember we first of all started looking at a pure pitching motion, right, and we got a second order equation from which we derived expressions for frequency and the damping of aircraft in pure pitching motion, right. And here we are making approximation saying that the change in forward speed is negligible and the motion is in pitch, right. What is happening here? So, is there any difference that you find between the two expressions? The only difference is the appearance of this term. Okay. So, earlier when we talked about the pure pitching motion, we did not have this Z alpha term, right. Of course, because the aircraft was constrained only to have pure pitching motion and not any other motion, right. So, that was an assumption that we use there. So, here the which, so this Z alpha is appearing which this thing gives us short period motion from a pure pitching right. An effect of that is that no, even though you have damped out the motion, short period motion due to these terms mq and m alpha dot, mq and m alpha dot are damping terms, isn't it, because rates are involved here. See, the pitch rate is involved here, alpha dot is involved, right, and those terms which are having rates involved, they are damping terms, right. So, even after this short period mode is damped out in pitching motion, because of this particular term, this term is like vertical motion with respect to change in angle of attack, that remains as a residual, and there are people arguing that this will probably result into an ensuing phugoid motion, right. So, there are other models, new models for short period and phugoid motion, where the phugoid is seen as an ensuing motion when the short period ends. Understand? Okay. Now, let us so what we have done is we have based on some approximations, we have come down to simpler models from where we have found expressions for damping and frequency, right, for phugoid and short period modes. Now, what we are going to do is we are going to take an example where we have a actual model, okay, with some numbers, right, and we are going to solve that on computer, find the eigenvalues, right, and see how close they are to the eigenvalues which we obtained from the approximations, right. So, we will carry out this exercise now. So, we have this this matrix given for a so A matrix is given. Remember, A matrix includes the geometric and aerodynamic properties of the aircraft about that equilibrium state, right. So, equilibrium state here is the same what we have been using so far. So, so this is my equilibrium state, okay, about which we have been given this linear model to study the perturbed behavior of aircraft. So, this is our A matrix, right. So, we have to find out the eigenvalues of this matrix, and that those eigenvalues are going to be exact, right. Now, I am solving an eigenvalue problem and on computer without doing any simplification. I am including all the parameters of aircraft here, right. So, I will get exact eigenvalues from this procedure. So, I am solving this eigenvalue problem on computer, right. The mathematical tools are available for doing this. So, the equation, quadratic equation that you arrive at is this. Lambda raised to 4 plus 5.05 lambda raised to 3 plus 13.2 lambda squared plus 0.67 lambda plus 0.59 equal to 0, right. Solution of this no is a pair of complex two pairs of complex conjugate eigenvalues. So, one pair is this lambda 1 and 2 minus 0.0171 plus minus this imaginary part 0.213 minus 2.5 plus minus 2.59 imaginary part. These are exact values, right. So, exact solutions. Can you identify which one is short period mode and which one is Fugate? The one lying close to the imaginary axis is the Fugate, right. We said short period is highly damped, so it should be lying far to the left in the complex plane, right. So, by looking at these eigenvalues, magnitude of these eigenvalues, I can say that this set is corresponding to the Fugate mode and this is corresponding to the short period mode, right. All right. So, these are exact numbers by solving that matrix for eigenvalue we have obtained this. So, we find that both these modes are oscillatory, right, because you have these eigenvalues which are complex conjugate, oscillatory and stable, right. So, let us try to what is the other way of identifying that this set is corresponding to phogoid and this corresponding to short period. So, short period is right now only related to short period, right. The literal meaning of short period is short period. So, frequency is high, is not it. Phogoid is long period motion. So, this eigenvalue actually results in long period long time period. So, let us list down now the characteristic parameters which define the aircraft per out motion corresponding to phogoid and the short period modes, and we will list down here the exact and the approximate values. So, approximate values are based on the formula that we derived using simpler explanation of physics, right. So, some of the parameters that normally people, this is the language in which you talk about the behavior of the motion. Time to half the amplitude, right, because it is a stable mode. So, amplitude is going to go decay, right, it is going to decay in time. So, this is time to half the amplitude. Is equal to this, right, 0.693 over the real part of the eigenvalue, right. Approximate value of this parameter is 30 seconds, which we obtained by using our formula, right, that we derived for the phogoid mode. Omega d is the damped frequency, right, frequency of the damped motion, and that will be given by imaginary part. So, this is the exact value approximate value, this is exact, whatever you see in the bracket is the approximate value, and the one with no brackets is the exact number. Number of cycles to half the amplitude is given by this eta is the real part and omega d is the imaginary part of the eigenvalue. So, this is the language in which you talk, right. So, how many cycles to have the amplitude, right. So, you have to speak in that language. So, you see quite a bit of difference between the exact value and the approximate value. So, what it tells you? What it tells you is that the approximation is not so good, isn't it? We made some assumptions while arriving at the approximate formula for the phugoid mode frequency and damping, right, from where we are getting all these numbers, right. The approximation involved was that delta alpha is change in angle of attack is 0, right, and that is resulting into giving me an error. No, this is like an error, that this is the exact value and this is the approximate value. So, there is a huge amount of error involved. What is the order of the error? It's roughly more than 20%, isn't it? So, this approximation was not so good, right, it was not good. Remember, approximations we are making assumptions and we are arriving at approximate formula to find the relation between these parameters and the design parameters, right. You want that to be very accurate, if it's not 100%, very close, so that you know which parameter is going to change the phugoid motion after the aircraft is made, right. Then only we can change that parameter at the design stage itself. So, the error involved here is quite large, right. Okay, let us look at the short period. right. So, T half here is the time to half the amplitude, which is 0.693 over the real part of the eigenvalue, and that is giving me 0.28 second, right. That is the exact number and this is the approximate value, right. This is very close, no, 0.28 and 0.278, very close. Look at the damped time period, which is 2 pi over omega d. Omega d is this 2.59 and that is giving me 2.42 seconds, which is the exact value, and 2.4 second is the approximate value. Cycle to half the amplitude, here we get 0.11 cycles exact, 0.16 cycles approximate, right. So, this is looking very close, is not it. So, the assumption that we made while arriving at approximate formula for the short period mode was quite good, I would say, right. So, error is very low here, which means assumptions involved arriving at short right. So, now if you want to find exact formula for both of them together, then you know that you have to solve a quartic equation, right, using symbolic tools. But you cannot get an idea of, if I, let us say I am able to retain all the parameters, not exactly giving them any number, is not it, and then want to arrive at expressions for eigenvalues for short period mode and the Fugite mode, then you know that you are going to get large expressions, right. You will have all kind of terms here, xu, xw and all that. In terms of those parameters, right, if you arrive at expressions for eigenvalues using exact method, then the expression is going to be large, it is a huge expression and it will depend upon eigenvalue will depend upon everything. Then a designer will not be able to understand which parameter is affecting which eigenvalue the most. That is what we can play with at the design stage. That is where arriving at simpler expressions is useful, right. But here we see that Fugite mode approximation was not good, right. There is too much of error involved here. If we approximation, the people have till recently also, even after 100 years of flight, been working on the approximate formulae, and the one recent article which talks about this says that we cannot really look at the two motions as decoupled motions, right. To start with, we assume that they are decoupled based on the location of corresponding eigenvalues in the complex plane, right. And then we started looking at the simpler models. So there are arguments based on that. What people have come down to is that this phugoid mode actually is an ensuing motion. It comes from the short period. So when short period ends, then you have this motion starting. Okay, just one more thing. Let us try to find out the eigenvectors, right. Eigenvectors are going to tell us about the directions in which the system is going to evolve, right. That is what we understand by eigenvectors. Let us look at the eigenvectors and then try to find out some regions for the errors that is involved here. So, I am trying to find out the eigenvectors corresponding to the short period mode and to the phugoid mode. And let us also try to non-dimensionalize the eigenvector. No, we have to keep some scale. Eigenvector is a general eigenvector, right. There is no exact number attached to it, it's with respect to something, right. So, what we do is we do some non-dimensionalization and look at the eigenvectors. So, phugoid short period eigenvalue So, what I am doing is I am assuming this delta theta to be 1, okay, and looking at other variables with respect to that, right. The size of this vector is 1 and with respect to that I am looking at size of other variables. Now, look at the magnitude of these quantities, right, with respect to this delta theta, which is of the size 1. Now, and also look at the corresponding values, two different values corresponding to two different modes. You see that magnitude of this is very low, short period mode corresponding to delta u, right. This number is very low. Take the magnitude of that value, this number, right, and look at the magnitude of this number. This is very large as compared to this. So, this gives me a reason to keep this delta u as non-zero for the Fugite mode, and we can assume this delta a to be 0 for the short period mode, right, and these are exact numbers, right. I am solving an eigenvalue problem and then I am arriving at this set of eigenvectors, right. So, this was a correct assumption that you can keep the delta u as a variable for the Fugite mode and probably neglect that delta u here in the short period mode, right, because this magnitude is very low as compared to this magnitude. Look at this delta alpha. Delta alpha here is very low, here is very large. So, keeping delta alpha as the variable in the short period mode was a good approximation. This delta q, which is non-dimensionalized with respect to c over 2 u naught, again in Fugite is very low, right. In short period as compared to Fugite is having a larger magnitude, right. So, using delta alpha and delta q for Fugite was kind of a good approximation, right, and dropping delta u. See, you can get better approximations if you have more and more terms in your equations, right, but solving an eigenvalue problem becomes difficult then, and even if you can solve them, you will arrive at an expression which is very difficult to interpret after that or make any sense out of that. It will be more difficult, right. In this column, the eigenvector corresponding to the Fugite mode eigenvalue, you see the magnitude of delta u and delta theta are large, right, and that was the reason when why we kept delta u and delta theta as important variables in Fugite mode, right, and here delta alpha and delta q, right. You understand the physical reason behind this? Now, this information is coming from the exact analysis. Any question? Try to look at now the variation of these eigenvalues in the complex plane when you change something on the aircraft, right, and one of the things that you can easily change is the CG, right. So, sometimes there will be a block of masses just for balancing out the aircraft, right. So, dead weights inside the aircraft which can be used to change the aerodynamic property of the stability property of the aircraft. So, to start with, my eigenvalues are located for wide mode, short period mode, right, and we want to change the CG, right. So, let us see what is the effect of changing CG on the eigenvalues. So, CG is moving aft, in this particular case, which means static margin is what we will do is we will stop here and we will continue from here tomorrow.